The purpose is to develop an AI agent capable of playing two-player Briskas in a partially observable adversarial environment. Apply Monte Carlo simulation to estimate move quality under uncertainty. Analyze the effectiveness of the agent through repeated tournament-style evaluation. Some of the key questions you can ask yourself is, can Monte Carlo simulation improve decision-making in Briskas compared to random play? How does Monte Carlo agents perform against a strong heuristic-based opponent? How does the number of simulations affect win rate, score difference, and computational cost? Can hidden information sampling provide the effective estimates of future game outcomes? Some of the concepts discussed in this project contain adversarial search, Monte Carlo rollouts, hidden information, heuristic agents, sequential decision making, utility evaluation, game simulation, and artificial intelligence agents.
For this experiment, information was gathered on several important concepts related to adversarial artificial intelligence and decision-making in competitive environments. One of the main concepts studied was the adversarial AI, which focused on environments where multiple agents compete against each other, and where one player's success negatively affects the opponent. Since our project was based on a competitive card game, understanding adversarial AI was essential for designing intelligent agents capable of making strategic decisions. Another important topic researched was hidden information and uncertainty in games. Because players cannot fully observe the opponent's cards or future game states, the AI must make decisions without complete information. This increases the complexity of the environment and requires the agent to estimate possible outcomes instead of relying on exact predictions. The project also explores Monte Carlo simulation techniques and stochastic games. Monte Carlo simulation helps the AI estimate the possible actions by repeatedly simulating many possible game outcomes and analyzing the results statistically. The approach is useful in environments that contain randomness and uncertainty because it allows the AI to evaluate future possibilities more effectively. Several tools and computational resources were used throughout the implementation. The project was developed in Python using the AIMA Python framework to structure the game environment and implement intelligent agents. NumPy was used for numerical operations and data handling, while Matplotlib was used to visualize experimental results and compare the performance of different agents. Finally, the experiment focused on evaluating how different agents perform under uncertainty and competition. This included comparing random heuristic and Monte Carlo-based agents using metrics such as win rate, score differences, and consistency across multiple simulated games. Overall, this information gathered provided a deeper understanding of how adversarial AI systems can make decisions in uncertain and competitive environments.
For the experiment set, we used a two-player version of Briskas. Player 0 was the agent being tested, and player 1 was the opponent. Three agents were compared. The random agent chose a legal card randomly. The heuristic agent used simple game knowledge, such as trying to win tricks and value high-point cards. And the Monte Carlo agent evaluated possible moves by simulating future games and choosing the move with the best average result. Each main experiment was run for 100 games. The metrics used were win rate, average points per game, and average scores difference between the two players. This is the main results tables from the main tournament. The Monte Carlo agent won 83% of the games versus against a random agent with an average score difference of 35 points. This showed that I performed much better than an IE baseline. And against the heuristic agent, the Monte Carlo won 63%. The margin was smaller, which makes sense because the heuristic agent is a stronger opponent. However, it still scored above 60 points on average. So I collected more than half of the available points. And the last row shows that the heuristic agent also defeats the random play consistently. This confirms that the heuristic agent is a valid stronger baseline. There's a graph showing the win rate with the dashed lines represent the 50% mark to show an even game. This is for the average point graph. And now this is for the Monte Carlo sample count. The experiment tested how the number of Monte Carlo simulations per decision affected the performance against the historic agent. With only 5 samples, the win rate was 52%, which is only slightly above the 50% reference line. With 10 samples, it increased to 72%, but with 20 samples to 80%. At 40 samples, it reduced sadly to 60%. This does not necessarily mean that 40 samples is worse, since BRCA has a random car deals and the simulations also include randomness, so some variation was expected. And this shows that trend, and with in the that too few simulations gives a weak estimate of the best move. As the number of samples increased, the Monte Carlo agent usually makes better decisions because it has tested more possible futures. However, more samples also require more computation time. For this project, 20 samples gave the best result, while 47 was still strong but slightly lower because of the randomness. The important conclusion is that Monte Carlo performance depends on the number of simulations, and there's a trade-off between decision quality and runtime.
In conclusion, this experiment demonstrated several important concepts related to adversarial artificial intelligence and strategic decision-making in competitive environments. One of the key takeaways was the adversarial AI allows intelligent agents to make strategic decisions while competing against other agents. The experiment also showed that Monte Carlo simulations are highly effective for handling uncertainty and hidden information, since the AI can estimate possible future outcomes throughout repeated simulations instead of relying on exact knowledge of the game state. Another important finding was that repeated simulations improved the reliability and consistency of performance evaluations. By running many games and comparing results across different scenarios, it became easier to analyze the strengths and limitations of each agent. The Monte Carlo-based agent demonstrated stronger decision-making abilities when compared to random and heuristic approaches because it was able to evaluate future possibilities more effectively. The experiment also highlighted how hidden information games increase the complexity of AI reasoning and strategy selection. Since the AI does not have access to all information, it must estimate probabilities and adapt in decisions under uncertainty. Additionally, several lessons were learned throughout the project. One lesson was that AI performance can be improved through statistical analysis of future outcomes. Another was that simulation-based approaches become especially useful when exhaustive search methods are impractical due to computational complexity. Finally, implementing adversarial agents require balancing computations time with decision accuracy in order to achieve effective performance in competitive environments.
We want to acknowledge the tools and resources that helped us complete this project. One of the biggest ones was AI MA Python because it gave us the base game framework we needed for things like legal move, utility functions, and terminal states. Even though we used that framework, out of the Briskas rules, the Monte Carlo logic, and the testing process were implemented by our team. We also want to acknowledge our AI course materials because they help us understand concepts like adversarial search and why Monte Carlo simulation was a better option than using something like Minimax for this game. For reference, our main source was Artificial Intelligence: A Modern Approach by Stuart Russell and Peter Norvig, along with the AI-MA Python repository and the UPRM engineering report guide that help us format the writing report correctly. Overall, these resources help us build both the technical and writing parts of this project successfully. Thank you.